What is quantum gravity? Imagine a world where the very fabric of space and time is woven from the threads of quantum mechanics. This is not just a theoretical exercise but a profound quest to understand the universe at its most fundamental level. This is the world that quantum gravity seeks to understand, a world where the force of gravity dances to the rhythm of the quantum world. In this realm, the smooth curves of spacetime envisioned by Einstein's general relativity are interwoven with the probabilistic nature of quantum mechanics. Quantum gravity is a theoretical framework that attempts to unify two of the most successful theories in physics, general relativity and quantum mechanics. General relativity, formulated by Albert Einstein, describes the universe on a large scale, explaining the behavior of stars, galaxies, and the universe itself. General relativity provides a comprehensive understanding of how massive objects like stars and planets warp the fabric of spacetime, creating the force we perceive as gravity. It has been tested and confirmed through numerous experiments and observations, from the bending of light around the sun to the precise orbits of planets. Quantum mechanics, on the other hand, governs the microscopic world of atoms and subatomic particles. It describes the strange and often counterintuitive behaviors of particles at the smallest scales, where particles can exist in multiple states at once and can be entangled over vast distances. While these two theories have been incredibly successful in their respective domains, they are fundamentally incompatible. The smooth, continuous space-time of general relativity does not mesh easily with the discrete, probabilistic nature of quantum mechanics. This incompatibility arises in extreme environments where both gravity and quantum effects are significant, such as inside black holes or at the moment of the Big Bang. In these scenarios, the predictions of general relativity and quantum mechanics diverge, leading to a breakdown in our understanding. Quantum gravity aims to bridge this gap and provide a unified description of all the fundamental forces of nature, including gravity, within a single, coherent framework. This would not only deepen our understanding of the universe but could also lead to new technologies and insights into the nature of reality itself. This is a monumental task, and despite decades of research, a complete theory of quantum gravity remains elusive. Scientists continue to explore various approaches, such as string theory and loop quantum gravity, in the hope of one day unlocking the secrets of this profound and mysterious force. To understand the significance of quantum gravity, we need to delve into the two pillars of modern physics, general relativity and quantum mechanics. These two theories have fundamentally reshaped our comprehension of the universe, each addressing different scales and phenomena. General relativity, developed by Albert Einstein in the early 20th century, revolutionized our understanding of gravity. Before Einstein, gravity was seen as a mysterious force acting at a distance, as described by Newton's laws. Einstein proposed that gravity is not a force acting at a distance, as Newton had envisioned, but rather a manifestation of the curvature of spacetime. This was a groundbreaking shift in perspective, suggesting that massive objects cause spacetime to curve, and this curvature directs the motion of other objects. Imagine a bowling ball placed on a trampoline. The ball creates a dip in the fabric, and any object rolling nearby will be deflected towards it. This simple analogy helps us visualize how massive objects like planets and stars warp the fabric of spacetime. This is analogous to how massive objects warp spacetime, causing other objects to be attracted to them. The more massive the object, the greater the curvature it creates, and thus, the stronger the gravitational pull. This revolutionary idea explained the anomalous precession of Mercury's orbit and predicted the bending of starlight by the sun's gravity, which was later confirmed during a solar eclipse. These observations provided strong evidence for Einstein's theory and marked a significant milestone in our understanding of the cosmos. Quantum mechanics, on the other hand, emerged in the 1920s and provided a completely different picture of the universe at the atomic and subatomic levels. It introduced a new framework for understanding the behavior of particles that are incredibly small, such as electrons and photons. Unlike classical physics, which assumes that particles have definite positions and momenta, quantum mechanics introduces the concept of wave-particle duality. This means that particles can exhibit both wave-like and particle-like properties depending on how they are observed. Particles can behave like waves, and their properties, such as position and momentum, are governed by probabilities rather than fixed values. This probabilistic nature is a core aspect of quantum mechanics, challenging our classical intuitions about certainty and predictability. This inherent uncertainty is a fundamental aspect of the quantum world and has been experimentally verified countless times. The famous Heisenberg uncertainty principle encapsulates this idea, stating that the more precisely we know the position of a particle, the less precisely we can know its momentum, and vice versa. This principle has profound implications for our understanding of reality at the smallest scales. While general relativity and quantum mechanics have been incredibly successful in their respective domains, they clash when we try to combine them. This clash arises because general relativity describes gravity as a smooth, continuous curvature of space-time, while quantum mechanics dictates that energy, and therefore gravity, is quantized, meaning it exists in discrete packets or quanta. This fundamental incompatibility becomes apparent in extreme environments where both gravity and quantum effects are significant. For example, at the singularity of a black hole, where gravity is infinitely strong and space-time is infinitely curved, general relativity breaks down. Similarly, at the moment of the Big Bang, when the entire universe was compressed into an infinitesimally small point, both gravity and quantum effects were dominant. In these extreme environments, we need a theory that can reconcile the smooth, continuous nature of gravity with the discrete, probabilistic nature of quantum mechanics. This is where quantum gravity comes in. Quantum gravity aims to provide a unified framework that can describe gravity at the quantum level, resolving the incompatibility between general relativity and quantum mechanics. Why is quantum gravity important? The quest for quantum gravity is not merely an academic exercise, it has profound implications for our understanding of the universe and the fundamental laws of nature. This pursuit is a bridge between the realms of the very small and the very large, aiming to unify the principles of quantum mechanics and general relativity. Firstly, a successful theory of quantum gravity would provide us with a complete and consistent description of the universe, from the smallest subatomic particles to the largest cosmic structures. This would mean a seamless understanding of how the universe operates on every scale, from the quantum level to the cosmological level. It would allow us to understand the universe at its most fundamental level, revealing the secrets of its origin, evolution, and ultimate fate. By comprehending these fundamental aspects, we could potentially unlock answers to age-old questions about the nature of existence and the forces that have shaped our cosmos. Secondly, quantum gravity has the potential to resolve some of the most perplexing mysteries in modern physics. These include the enigmatic phenomena that have puzzled scientists for decades and continue to drive research and debate in the scientific community. For example, the nature of dark matter and dark energy, which together constitute about 95% of the universe's energy density, remains unknown. Understanding these components is crucial, as they play a significant role in the structure and expansion of the universe. Some theories suggest that these enigmatic entities could be explained by quantum gravitational effects. If proven, this would revolutionize our comprehension of the universe's composition and the forces at play. Moreover, quantum gravity could shed light on the information paradox, which arises from the conflict between general relativity and quantum mechanics regarding the fate of information that falls into a black hole. This paradox challenges our understanding of how information is preserved in the universe. General relativity predicts that information is lost inside a black hole, while quantum mechanics dictates that information cannot be destroyed. This contradiction has led to intense debates and numerous theoretical proposals aimed at resolving the paradox. A theory of quantum gravity would need to reconcile these seemingly contradictory principles. Achieving this would not only solve the information paradox but also pave the way for a unified framework that could describe all fundamental forces and particles in the universe, leading to a deeper and more comprehensive understanding of the cosmos. The search for a theory of quantum gravity, often referred to as the search for a theory of everything, has been a major driving force in theoretical physics for decades. Numerous approaches have been proposed, each with its strengths and weaknesses. Some of the most prominent candidates include string theory and loop quantum gravity. These theories, while still under development and lacking experimental verification, offer intriguing glimpses into the potential nature of quantum gravity. String theory, a universe of strings. String theory, one of the leading contenders for a theory of quantum gravity, proposes that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings are incredibly small, far smaller than anything we can currently observe with even the most powerful microscopes. Just as the different vibrations of a violin string produce different musical notes, the different vibrations of these fundamental strings give rise to the different particles and forces we observe in nature. One of the most remarkable features of string theory is that it naturally incorporates gravity. In string theory, gravity is not a separate force but rather an emergent property of the vibrations of these fundamental strings. This elegant unification of gravity with the other fundamental forces is a major achievement of string theory. However, string theory is not without its challenges. One of the main criticisms is that it requires the existence of extra spatial dimensions beyond the three we experience in everyday life. These extra dimensions are thought to be curled up at incredibly small scales, making them undetectable by current experiments.